Good morning. We have been discussing a particle in a potential well or a particle in a box, where we have a particle which is confined to a region 0 to a along the x axis, and the confinement is achieved by having two infinitely large potentials, one at x equal to 0 and one at x equal to a. So, the particle cannot move to smaller values of x, neither can it move to larger values of x. It is confined in this region, and we know that the wave function of the particle has to vanish at x equal to 0 and x equal to a. And we had in the last class worked out what the allowed wave functions are, the allowed energy levels are, and we found that there are only a discrete number of energy levels which are allowed, and these energy levels are quantized in the sense that there is one energy level corresponding to every integer 1, 2, 3, 4, 5, 6 all the way to infinity, and the energy level corresponding to any integer n is n square pi square h cross square by 2m a square, and the corresponding wave function psi n. So, corresponding to every n there is also a different wave function. It is some normalization coefficient which we had also worked out. The normalization coefficient a n is the same for all values of n, and it was, we found that it is square root of 2 by a, and then we have the time dependent part e to the power minus I e n t by h cross, and the spatial part sine n pi x by a. So, we had worked out these wave functions, this energies and the amplitude normalization coefficient in the last class. In today's class, let me take up a few for discussion, a few problems related to a particle in a potential well. So, we will now take up a few problems on a particle in a potential well. The first problem is a situation. So, the first problem is a situation, problem number 1, where we have an electron is confined in a potential well of length 10 angstrom. And the question is, we have to find the energy of the ground state, the first excited state and the second excited state. So, the question calculate E1. E1 is the energy of the ground state, E2 the first excited state, E3 the second excited state. Now, the energy, the ground state energy, we have, I just showed you the formula. E1 is, let me show you the formula again. The energy corresponding to the nth energy level is n square pi square h cross square by 2m a square. So, for n equal to 1, this is pi square h cross square by 2m a square, and we also know that h cross is h divided by 2 pi. So, when I square it, I will have h square divided by 4 pi square, the pi will cancel out. So, we can also write this as h square divided by 8 m a square. We have to put in the values. So, this h we know has a value 6.63 into 10 to the power minus 34 joules second. I am not showing the units explicitly. 8. The mass of the electron we know is 9.1 into 10 to the power minus 31 kg. I am not putting the units explicitly again, and this length, the dimension of the potential well or the dimension of the box is 10 Armstrong. 10 Armstrong is 10 to the power minus 10 meters, minus 9 meters. 1 Armstrong is 10 to the power minus 10 meters. So, this into 10 to the power minus 18, and that is 10 Armstrong square. So, we have to calculate this, and this comes out to be 6 into 10 to the power minus 20 joules, approximately 6 into 10 to the power minus 20 joules. So, this is the ground state energy, the lowest energy that an electron in a potential well of dimension 10 Armstrong can have. Now, next we will calculate the energy of the first excited state. So, the first excited state E2, first excited energy level, has an energy which is n square into the ground state energy, n being 2. So, we have the first excited state has an energy 4 times E1, which is 2.4 into 10 to the power minus 19 joules. Similarly, the third energy level or the second excited state has an energy proportional to 3 squared, that is 9 times E1. So, this is 9 times 6 is 54. So, 5.4 into 10 to the power minus 19 joules. So, we see that we have these 3 energy levels. The first one is E1, then we have 2, and here we have 3, and we have these higher and higher energy levels. Now, the next part of the problem, we have an electron which is in the first excited state, and the electron falls to the ground state, jumps to the ground state, and the difference, the difference in energy is radiated out as a photon. So, pictorially we can represent this as follows. There is an electron here. The electron goes from the first excited state to the ground state, and in this process a photon comes out. The question is, find the wavelength of the photon. So, the electron jumps from the first excited state to the ground state. It goes from a higher energy to a lower energy. The excess energy comes out in the form of a photon. The problem is to calculate the wavelength of this photon. So, the difference in energies delta E is the energy of the photon that comes out. So, the difference in energy is the energy of the first excited state, which is 4 into E1. The energy of the first excited state, remember, is 4 into E1, and E1 is, let me write it in terms of E1 here, E1 minus E1. This is the difference in energy this is the difference in energy between the first excited state and the ground state, delta E. It is 4 E1 minus E1, and this is the energy of the photon. We know that the energy of a photon is h nu, h times the frequency, which we can also write as h c by lambda. So, the energy of the wavelength of the photon, if it is lambda that is emitted, if it is lambda, then the energy of the photon is h c by lambda. So, this is the difference in the two energy levels, and this should be equal to the energy of the photon. And we know that E1, so we can write this 4 minus 1 is 3. So, we can write this as h c by lambda is equal to 3 and 3 times E1, E1 is h square by 8 m a square. So, this is equal to 3 h square by 8 m a square. From this we see that the wavelength lambda of the photon that comes out. So, 1 h cancels out, we have 8 by 3, 8 divided by 3, and then we have m c by h into a square. Now, we have encountered this combination m c by h. If you remember, when we discussed Compton scattering, in this Compton scattering process, the shift in the wavelength is the Compton wavelength into a factor of 1 minus cos theta, where theta is the scattering angle. And remember that the Compton wavelength, the shift in the wavelength which decides the amplitude, the magnitude of the shift in the wavelength, was h divided by m c, where m was the mass of the electron. So, here we have the factor m c by h. So, we can identify this as the inverse of the Compton wavelength. So, we can write this as 8 by 3, the size of the potential well squared, the length of the potential well squared, divided by the Compton wavelength. And remember that the Compton wavelength was 2.4 into 10 to the power minus 12 meters. We had calculated this, and A is 10 to the power minus 9 meters. So, we have 8 by 3, and here we have 10 to the power minus 18 divided by 2.4 into 10 to the power minus 12. So, finally, the result is the wavelength of the radiation that comes out is of the order of 1 micrometer. So, what we see is that in this problem, where we have an electron that is confined in a potential well of dimension 10 angstrom, and where, so the electron is confined to a potential well of dimension 10 angstrom, and the electron jumps from the first excited state to the ground state. The energy that is released, the photon which carries away this energy, has wavelength 1 micrometer. Let us ask the question, what part of the spectrum is this photon going to be? Now, 1 micrometer is in the infrared. So, if I have a potential well of dimension 10 angstrom and I have an electron trapped in this, which I could possibly have in a semiconductor, by in a quantum well in a semiconductor, the photon that is going to be emitted when the electron jumps from the first excited state to the ground state, that photon is going to be in the infrared. So, a 10 angstrom potential well is going to produce the first excited state to ground state transition is going to produce a photon which is in the infrared. let us ask the question, what should we do if I would like to have a potential well which produces radiation in the ultraviolet? How will you manipulate the potential well so that the radiation comes out in the ultraviolet? Now, if you want to increase the frequency or decrease the wavelength, you have to play around. There is only one thing that you can play around here, it is the width of the potential well. So, if you reduce the width of the potential well, which if you can reduce this, then the wavelength of the emitted radiation is going to go down and you can reach the optical range, provided you can make your potential well much smaller. Okay, so, in this problem what we have done is we have got a feel for the numbers involved in these particles when you have a particle in a potential well, and when you have an electron, the energy levels are of the order of 10 to the power minus 19 joules, and for a potential well 10 angstroms width wide, and the first excited state to ground state transition, the energy difference corresponds to a wavelength of photon of wavelength 1 micrometer. Okay. Let us now consider the second problem to do with potential wells. So, again we have a potential well, second problem. We have a potential well of length L, and we have already seen that in this potential well you can have many different stationary states for a particle. So, the ground state psi 1, this is the lowest energy state, we have worked this out. The ground state wave function is going to be root 2 by L e to the power minus I E1, where E1 is the energy corresponding to the ground state, into T by H cross into sine pi x by L, and then we have the first excited state psi 2. This is going to be the same normalization coefficient. The time dependence is now going to be e to the power minus I E2 T by H cross, and we have sine 2 pi x by L. And then you have the second excited state psi 3, 4, 5, etc. So, these are the stationary states which if there is a particle in this state in the psi 1, then the probability density of the particle does not change with time, and if I make a measurement of the energy of the particle, I will get a value E1. If there is a particle in this state psi 2, then again the probability density of the particle does not change with time, and if I make a measurement of the energy, I will get E2. So, these are the stationary states or the energy eigenstates. Now, in this problem we are going to consider a state psi function of x and t, which is 3 by 5 psi 1 x t plus 4 by 5 psi 2 x t. So, this wave function is a linear superposition of the ground state and the first excited state, and we know that this is also a solution, allowed solution of for a particle in a potential well, because this is a solution, this is also a solution, and since the differential equation governing psi is linear, so any linear superposition of solutions is also a solution. So, this is also a solution for a particle in a potential well. Now, this solution is not a stationary state, if you calculate the probability density, you will find that it is not going to be independent of time, it is going to change with time. The question is, first question, the first question is, what happens if you make a measurement of the energy of the particle? So, if I measure the energy of the particle, so there is a particle whose in a state which is described by this wave function, and the question is, what happens if I make a measurement of the energy of the particle? Now, remember, if the particle had been in this state, I would have got an energy E1. If the particle had been in this state, I would have got energy E2. But now the particle is in a superposition of these two states. This state, let us see what happens when, so, okay. What happens when we measure the energy? So, you have to, there corresponding to energy, there is the operator, the Hamiltonian operator H, I H cross del by del T of, this is the Hamiltonian operator. So, let us see what happens when the Hamiltonian operator acts on this wave function psi. So, let us see what happens when the Hamiltonian operator acts on this wave function psi, because corresponding to energy there is this, corresponding to every physical dynamical variable in quantum mechanics there is an operator, and I have told you that corresponding to energy there is the Hamiltonian operator. So, let us see what happens when the Hamiltonian operator acts on this wave function psi. Now, the Hamiltonian operator is I H cross del by del T. when this operator acts on psi 1, the time derivative is going to give me a factor of minus I E1 by H cross, and minus I E1 by H cross into I H cross will give me E1. So, the Hamiltonian operator, the time derivative, that operator acting on this is going to give me E1 into the same thing. This is an eigen function of the Hamiltonian operator, and we will have E1 into 4/5 into psi 1 plus if the Hamiltonian operator acts on psi 2, it will give me E2, because when I take the time derivative of this, I am going to get minus I E2 by H cross, and again multiplying with these factors I will get E2. So, this is going to give me E2 4/5 psi 2. Now, let us ask the question, is this wave function psi an eigen function of the Hamiltonian? A wave function is said to be an eigen function if H psi gives you a number lambda into psi itself. Now, psi, remember, is this 3/5 psi 1 plus 4/5 psi 2. H acting on psi gives us E1 3/5, this should be 3/5, sorry, E1 3/5 psi 1 plus E2 4/5 psi 2. So, you see that there is no way I can write this as a number into psi again, because there is an E1 which comes here and E2 which comes over here. So, what we can say is that this wave function psi, which is a superposition of psi 1 and psi 2, is not an eigen function of the Hamiltonian operator. So, it is not an eigen function, but it is a linear superposition of these two eigen functions. So, what we can say is that whenever we make a measurement of energy, you are going to get either E1 or E2. If I get E1 as my outcome, after the measurement the wave function is going to change from here to psi 1. If I get E2, the wave function after the measurement is going to be psi 2. And we can also calculate the probabilities of getting E1 and E2. So, the probability of getting E1, let us call it P1, so we want to calculate the probability of getting the value E1 as my outcome if I make a measurement of the energy for a particle in this state. Now, this state is a superposition of the eigenfunction corresponding to E1 plus the eigenfunction corresponding to E2. So, I can have two possibilities, either E1 or E2, and the probability of getting E1 is the mod square of this coefficient of psi 1. So, the mod square of this is 9 by 25 divided by the mod square of this plus the mod square of this. The mod square of this is 9 by 25 plus the mod square of this is 16 by 25 and the denominator is 1. So, the probability of getting P1 is 9 by 25. Similarly, we can ask the same question for E2, and the probability of getting an outcome E2, I am denoting that by P2, is the modulus square, the modulus of this coefficient, the square of that divided by the sum of the square modulus square of this plus the modulus square of this, that we have seen is 1. So, the probability of getting E2 is just the modulus square of this, which is 16 by 25. So, the probability of getting E2 is 16 by 25. So, if I have a particle in this in a state which is described by this wave function, and if I make a measurement of the energy, I will get either E1 or E2. The probability of getting E1 is 9 by 25, the probability of getting E2 is 16 by 25. Now, let me ask the next question. The next question is, what is the expectation value of the energy? Let me remind you what I mean by the expectation value. If I repeat the experiment many times, in the sense that I have many replicas of the same particle in the same wave function, and I measure the energies for all of these replicas, each time I do the experiment, I will get either E1 or E2. The question is, by expectation value, I use the mean. So, every time I will get either E1 or E2 with different probabilities. The question is, what is the mean energy, or if I do the experiment only once, what is the value of energy that I expect to get? The mean energy, the mean over all of these different replicas is what is going to tell us what value we expect to get. So, the question is, how can we calculate this mean value or the expectation value of the energy? Now, we know that we have already calculated this, that you have only two possible outcomes, E1 or E2, and the probability of getting E1 is P1, which is 9 by 25, the probability of getting E2 is 16 by 25. So, the average outcome, the mean outcome, the mean energy, the expectation value, this can be calculated as E1, the first outcome, into the probability of the first outcome, plus E2 into the probability of the second outcome. So, E1, we know it has a value, the probability of getting that is 9 by 25. E2 is 4 times E1, we have seen this already. So, 4 E1, and the probability of getting E2 is 16 by 25, and 4 into 16 is 64, 64 plus 9 is 73. So, the mean outcome, mean and value of the energy, the expected value of the energy is 73 by 25 into E1. So, it is approximately 3 times E1. So, we see that the mean value of the energy will be somewhere between E1 and 4 times E1, which is E2, somewhere in between, and this is the expectation value. This is the expected value of the energy. Now, we could calculate the expectation value of the energy in a different way also. So, we have, let me remind you of the other method in which we could do it. The energy, the expectation value of the energy could also be calculated in this way. Remember that for any physical variable, any dynamical variable, if I ask you the question, if I have many replicas of my particle and I measure that quantity, for example, position or momentum, if I make a measurement of the quantity, in general each time for in each replica I will get a different value. Here I will get E1 or E2, I cannot predict for sure which one I will get. So, in general, say momentum, position, I will get some spread different values, and if I ask the question how to predict the mean outcome or the expected value. So, what we have to do is we have to take the wave function psi corresponding to that state, take its complex conjugate, then write the operator corresponding to that physical variable. So, here the operator is the Hamiltonian operator H and act on psi and then integrate over dx. So, this will give me the mean value. So, let us calculate this and see that we get back the same answer. So, how much is psi star? We have to put in these values for psi and psi star and then act with the Hamiltonian operator on this and then do the integral. So, here we have calculated H into psi. H into psi is E1 into 3/5 psi 1 plus E2 into 4/5 psi 2. So, I can put that in straight away. So, I have the integral and here I will write the expression for psi star. I am now writing H psi, I am writing out this part. So, H psi is E1 into 3/5 psi 1 plus E2 into 4/5 psi 2 dx, and here I have to write psi star. So, psi star, remember that psi, the wave function psi, was 3/5 psi 1 plus 4/5 psi 2. So, if I take complex conjugate, I will get complex conjugate of this and this. So, when I take the complex conjugate of psi, I will have 3/5 psi 1 star plus 4/5 psi 2 star. So, I have to now multiply this. This is psi star, this is H, the Hamiltonian operator acting on psi, which I have written down here, and I have to do the integral over dx. So, I have to do this integral. The range of the integral is 0 to L, and the wave function and its complex conjugate both vanish for x less than 0 or greater than L. So, we have to now do this integral, that will give me the expectation value of the energy. Now, when I multiply these two terms, there should be a closing bracket here. When I multiply this with this, I will have one term which is psi 1 star into psi 1. Now, remember that we have normalized the wave function, that is 0 to L psi 1 star psi dx is 1, because when I multiply psi 1 with its complex conjugate, the time dependence part and its mod complex conjugate give me 1. This will give me a factor of 2 by L, and I will have sine square pi x by L. If I integrate sine square pi x by L from 0 to L, that integral multiplied by 2 by L is going to give me a factor of 1. That is how we have chosen this normalization constant, so that the integral of psi star psi gives me 1. Similarly, for this also the integral is going to give you a factor of 1. This comes from the total fact that the total probability of finding the particle in this state is 1. For this, the total probability of finding the particle is 1, or if the particle is in this state, again the total probability of finding the particle somewhere is 1. So, both of these functions have been normalized in the sense that the coefficient, the amplitude has been chosen, so that this is satisfied. Now, so there will be, these are the two terms when I have, which arise when I multiply these two, psi 1 star into psi 1, psi 2 star into psi 2. But there will also be cross terms. So, there will be a term of this type 0 to L psi 1 star psi 2 dx. Now, remember what psi 1 and psi 2 are again. So, psi 1, the spatial dependence is sin pi x by L, psi 2 is sin 2 pi x by L. So, the product of this sine and this sine term can be written as a sum of cosines. I can write this as a sum of two cosines, and both of these cosines, when I integrate from 0 to L, are going to give me 0. So, this is equal to 0, and so is the other cross term. So, all the cross terms are going to give me 0, and only the terms where I have multiplying a wave function with its own complex conjugate gives me 1. This is very similar to what you have when you deal with matrices and vectors. If you have a matrix and work out its different eigen values corresponding to each different eigenvalue, you will have an eigenvector, and you can check that the eigenvectors corresponding to two different eigenvalues will be orthogonal. Exactly the same thing happens here. The eigenfunctions corresponding to two different eigenvalues are orthogonal in the sense that psi 1 star psi 2 dx is going to be 0, and so is 0 to L psi 2 star psi 1 dx. So, now when I do this integral, I multiply these two and do the integral, I will get one term which is E1 into 9 by 25. The integral psi 1 star psi 1 dx is going to give me 1. So, that is going to be one term. So, let me write it down here. So, E1 9 by 25 is what arises when I multiply this and do the x integral. When I multiply this with this, I will get E2 16 by 25. E2 comes from here, and I have 4 by 5, 4 by 5. This integral is 1. So, what I get is this plus E2 16 by 25. And the other two terms where I have E1 psi 1 and psi 2, psi 1 star psi 2 or psi 2 star psi 1, the integrals are 0. So, this is the expectation value of the energy, and this is exactly the same expression which you had obtained when you had done the calculation earlier. So, we see that whichever way you calculate the expectation value of the energy, either you put in the operator psi, act on psi, psi star, you will, or if you calculate the probabilities of getting both these two values and calculate the expectation value. Either way you get exactly the same answer. Let me next take up the question, what happens if I make a measurement of the momentum of the particle? Let us ask the same question for the momentum of the particle. So, let us look at each of these states individually and ask the question, is this state an eigenfunction of the momentum operator? So, the spatial dependence of this function is sin pi x by L, and the momentum operator P is minus I h cross del by del x. And let us calculate this, P acting on psi 1. So, we are considering a situation where there is a particle in the ground state, and we want to ask the question, is the ground state an eigenstate of the momentum operator of momentum? So, if there is a particle in the ground state and I measure its momentum, what is the result going to be? If it is an eigenstate, you can make a definite prediction. If not, you can only predict expectation values, probabilities, etc. So, what we are doing now is we are checking if it is an eigenstate or not. So, momentum acting on psi 1 is what we wish to calculate. The momentum operator is minus I h cross del by del x. The wave function psi 1 has these two things which have no x dependence. So, I can write them, okay, let me write them anyway instead of being lazy. E to the power minus I E1 t by h cross acting on sin pi x by L. Now, when I differentiate with respect to x, these are as good as constants. So, I have to only differentiate this, and when I differentiate it, what I get is going to be minus I h cross pi by L is going to come out. So, I have minus I h cross pi by L into root 2 by A into e to the power minus I E1 t by h cross cos pi x by L. So, what we see is that when the momentum operator acts on the ground state wave function for a particle in a potential well, the ground state wave function is sin pi x by L, that is the x dependence. When the momentum operator acts on this, it changes it to cosine pi x by L. So, the ground state is not an eigenstate of the momentum operator. So, you cannot make a definite prediction as to what the momentum is going to be if I make a measurement of the momentum for a particle in the ground state of a particle in the box, or ground state of the energy states for a particle in the box. Now, let us ask the question, what is the expectation value of the momentum? We cannot predict a definite value. Can we predict what the expectation value is going to be? If I repeat the experiment many times for the same state. So, I have many replicas of particle in the ground state of a potential well, of the same potential well, and I measure the momentum, what is the expectation value? So, we have discussed how to calculate the expectation value. So, the expectation value of the momentum P has to, for the ground state has to be calculated like this, psi 1 star the P operator into psi dx. The integral has to be done from 0 to L. So, the psi 1 wave function, remember, it has this constant, it has this time dependent part, and when I multiply psi with psi star, the constant is not going to change, and psi star is going to give me 2 by L, it's going to get squared. When I multiply this with its complex conjugate, I am going to get 1, and I have sine pi x by L over here. So, this is going to give me 2 by L 0 to L. Psi star is going to give me sine pi x by L, and the momentum operator acting on psi 1 is going to give me this extra factor into cos pi x by L, and the extra factor is a constant minus I h cross pi by L cos pi x by L dx. Now, note that sine of pi x by L into cos of pi x by L, this integral dx is 0, because this is going to give me sine 2 pi x by L, half of that, and so this is going to give me sine and the cosine term both, and if I do this integral I will get 0, because it is going to give me cos, and this is one whole period of this function. If I integrate either sine or cos over a whole period, I get 0. So, this the expectation value of the momentum turns out to be 0. So, what we have been calculating now is that if I have a particle in the ground state, I am not bothering about this superposition or this. If there is a particle in the ground state and if I measure its momentum, what is the expectation value? And what we see here is that the expectation value of the momentum for a particle in the ground state, the expectation value of the momentum is 0. Each time I repeat the experiment, I will get different values. They will occur with equal probability for positive and negative, and the average is going to be 0. Now, if I have a you can check that also for psi 2, again when I act with momentum, I have a sign here. If I act with the momentum operator, it will give me cos. So, it is not an eigenstate, and if I calculate the expectation value of the momentum, I will have again cos into sine, the integral is 0. So, for psi 2 also the expectation value of the momentum is 0. So, from there we can say that for this superposition also the expectation value of the momentum is 0. For that matter, for any state of a particle, any superposition of such states of a particle in a potential well, the expectation value of the momentum is always going to be 0. Now, the next thing that we can calculate, let me tell you what that is. So, I have a particle, we will again restrict our attention to the ground state. I have a particle in the ground state in a potential well, and we have seen that the ground state is not an eigenfunction of the momentum operator. So, whenever I make a measurement of the momentum, I will not get the same answer every time, I will get different values, but the expectation value of the momentum is going to be 0. So, I will get positive and negative values with equal probability, and the outcomes are going to be such that the mean is going to be 0, the expected value is 0. But I am not going to get 0 every time I make a measurement. So, this basically tells us that the momentum is going to have a spread in the values. So, what we would now like to calculate is the uncertainty in the momentum, and I have told you how to calculate the uncertainty. In any quantity. So, the way to calculate the uncertainty in any quantity is you have to basically calculate the variance. So, what you have to do is you have to calculate the deviation from the mean, take the square of that and calculate its average. So, for the momentum you have to calculate the deviation. Every time you make a measurement you will get a different value which is not the average value. So, take the square of that deviation, mean square deviation, and I have shown you that this can be also written as the expectation value of p square minus the square of the expectation value of p. This I have shown you that this can be written in this way. Now, in this particular problem where there is an electron, a particle in the ground state, we have already calculated the expectation value of the momentum, and the expectation value of the momentum we have seen turns out to be 0. The expectation value of the momentum for a particle in the ground state of the turns out to be 0 for that potential well problem. So, we have already calculated this is 0. So, we now have to just calculate the expectation value of p square. So, the expectation value of p square can be calculated like this. I take psi star, I take the operator p and square it, and then act on psi and do this integral. So, we now have to calculate p square acting on psi, where we are dealing with the ground state wave function. So, I can write psi 1. Now, I have already calculated p acting on psi 1, and p acting on psi 1 is minus I h cross pi by L into these factors. This is a constant, this is a time dependent part of cosine pi x by L. Now, this is the momentum operator. So, if I act with the momentum operator, that is if I differentiate this, so what I have to do now is calculate p of p psi. This is what we mean by p square psi 1. So, I have to act with the momentum operator twice on psi 1. So, I act with it once and then act with it again. So, if I differentiate cosine with respect to x, I will get minus pi by L into sine, and that minus pi by L if I multiply with minus I h cross. So, what I will get is minus I h cross pi by L. This is already there here, and then I have one more factor of minus I h cross, and I have minus pi by L now, because when I differentiate cosine I will pick up a minus sign. So, this into I h cross pi by L, and then I have these factors root of 2 by a e to the power minus I e1 t by h cross, and I have the sign pi x by L, and minus I h cross pi by L into I h cross pi by L, this into this. So, minus I into I gives me a factor of 1, and I have h cross square pi square by L. So, what we see is that this can be written as psi 1 star, and p square acting on psi 1 is essentially pi square h cross square by L square. This minus I and I give you factor of 1 into psi 1 itself. This thing is psi 1 itself. So, this is pi square h cross square by L square psi 1. So, p square acting on psi 1 gives me the same. So, same wave function psi 1 again multiplied by this number pi square h cross square by L square, and I have to do this integral dx. Now, this is a constant, and we know that psi 1 star into psi 1 dx is 1. So, what we can say is that this will give me pi square h cross square by L square. So, the uncertainty in the momentum is the square root of this, that is the uncertainty in the momentum, and the square root of this is the square root of this. So, what we see is that the uncertainty in the momentum delta p is equal to the square root of this, which is pi h cross by L. So, in today's lecture we have solved a few problems, and I have shown you how to manipulate with some of these ideas and formulas which we have derived in the last few lectures.